So up to this point, we've been talking about transformations. Now we specifically want to talk about a linear transformation. And linear transformations are what we've already been dealing with, and they are the kinds of transformations we're going to continue to deal with. And we've already been using the definition of a linear transformation, but we haven't stated it explicitly, and it's important for us to understand what a linear transformation actually is. So a linear transformation is already somewhat familiar to us. Oftentimes we call it T, and we say that it maps from, we'll just say some Rn space to some Rm space, and we just use different letters to distinguish between one space and the other. Sometimes n is going to be equal to m, like when we transform from R2 space to R2 space, and sometimes n and m are going to be unequal, like when we might transform from R3 space to R2 space. When a transformation is a linear transformation, it also follows these couple of properties. So if we say that we're taking the transformation of the sum of two vectors, so let's say the sum of the vectors a and b, remember that when we add two vectors, we get a third vector. So here we're just saying that we're transforming a vector here, but it happens to be the sum of these other two. This is equivalent to taking the sum of the individual transformations. So this is the same thing. It's going to give the same result as the transformation of the vector A individually plus the transformation of the vector B individually. And linear transformations also follow this pattern where if we take the transformation of a vector that's scaled by some scalar, so let's say C times the vector A, that's equivalent to pulling the scalar out in front and saying that's the scalar times the transformation of that same vector A. When the transformation does these three things, it's called a linear transformation. And when it is a linear transformation, that is when we are allowed to express the transformation as a matrix vector product. And that's what we've already been doing, because we've been saying that if we have some subset here and some subset here, and we call this one A and we call this one B, we've been saying that the transformation T maps from A to B, and then we've been going on to say that we can express T as some transformation matrix, and so maybe we call T 1, 0, 2, 3, something like that, and we multiply it by a vector in A to get a result that is a vector in B, because the transformation is mapping vectors in A to vectors in B. Well, notice here that we're just expressing the transformation T as a matrix vector product. We're saying that this is the transformation matrix T. We're multiplying that by some vector A, and we're getting the vector B as a result. So we've already been doing this. We've already been dealing with linear transformations. We just haven't called them out or defined them that way. But this is a really, really key thing because we're going to be working with linear transformations all the time. And it's critical that we understand that when we have some transformation mapping vectors from some subset A to some subset B, that we're going to constantly be expressing that transformation as a matrix vector product. So we're going to take that transformation and we're going to write it one way or another as some matrix multiplied by some vector that's in this first subset that we are transforming from. So let's give an example here of how we express a transformation as a matrix vector product and kind of the idea behind that. So if we have, for instance, let's say that A is in R2, and let's say that the transformation T is mapping vectors from A into B, and B is in R3. So we're going across spaces here with our transformation. That means that we're going to have some transformation like this. We're going to put into the transformation two-dimensional vectors. So let's say we have A1 and A2 as our vector components for the vector in A. And when they come out in B, in R3 space, they're going to look like this. We're going to have something like negative A1 plus 2A2 for the first component. We'll have A2 minus 3A1. And then we'll have A1 minus A2 for the second and third components. So this equation here tells us what the transformation is doing. if I have a vector, let's say it's the vector 1, 2, that means A1 is 1, A2 is 2. If I plug those values into this expression over here on the right, I'm going to get -1 plus 4, or 3. I'm going to get 2 minus 3 times 1, or 2 minus 3, that's a -1. And then I'm going to get 1 minus 2, that's a -1. So this transformation, for example, would map the vector 1, 2 in R2 to the vector 3, -1, -1 in R3. And I could plug any vector from A, from R2 space, into this transformation, and the transformation is going to tell me what vector comes out in B. So this is giving me the pattern, but what I really want to do is be able to express this as a transformation matrix so that I have a matrix I can use to multiply by any vector in A. In order to get that matrix, all I have to do is look at what the transformation is doing to the standard basis vectors. So in this case, we're transforming from R2 space. We always have to think about which space we're transforming from, because that's the one we're going to think about. So we're transforming from R2 space, and the standard basis vectors for R2 are I and j. So I is the vector 1, 0, and j is the vector 0, 1 in R2, the space we're transforming from. So all we need to do is use this right-hand side here to figure out what is happening to I and j. So in order to figure out what's happening to I, the vector 1, 0, we'll just plug 1, 0 into this transformation here. So we'll say t of the vector 1, 0 is going to be equal to, and then we'll plug in here. So we'll get -1 plus 2 times 0. We'll get 0 minus 3 times 1, and we'll get 1 minus 0. And the result there will be -1, -3, and 1. And then we need to figure out what t is doing to j, the vector 0, 1. And we're going to get there when we plug into the right-hand side. We'll get -0 plus 2 times 1. We'll get 1 minus 3 times 0, and we'll get 0 minus 1. And so the result there is 2, 1, and -1. And then it's truly just as simple as these two become the column vectors of our transformation matrix. So this transformation here can really be expressed as, we'll say t equals the matrix here. First we take the transformation of I, which was this first step, so -1, -3, 1. And then the transformation of j, which was the second one we did there, so 2, 1, -1. And this is this same transformation, but expressed as a matrix. And now to transform any vector that we want to in A, we just take this matrix, we multiply it by the vector A that we want to transform, and that matrix multiplication problem will give us the vector B that we're transforming to. And so really, the transformation problem just turns into a matrix multiplication problem. So to get an idea of how we can actually use this to move figures in space, let's consider that we have some figure like this one. And it looks like we have the vertices of this quadrilateral here. This looks like it's at 4, 1. This is at 1, 2, 3, 4, 0, 4. This is at -3, 2. So -3 and 2. And this here is at 1, -2. So we have the vertices of the quadrilateral. And let's say we want to apply a transformation to this quadrilateral. Let's maybe say that we want to flip it across the y-axis. And then after that, we want to flip it across the x-axis. And we want to use a transformation matrix to roll all of these transformations up into one thing so that we can just multiply that matrix by any position vector that expresses one of the vertices of this quadrilateral and move the whole quadrilateral all at once. In order to do that, we need to think about a generic vector. So let's say the vector xy. If we want to flip a vector over the y-axis, that means that the x component will either change from positive to negative or from negative to positive. We're reflecting over this y-axis. So for instance, this -3 right here would move to the other side and become +3, or this +4 right here would move to the other side and become -4. In other words, we're just multiplying the x value by -1. So in order to accomplish this flip across the y-axis, we multiply x by -1. And then in order to accomplish the flip across the x-axis, similarly, we would multiply the y component by -1. Because if we flip across the x-axis, imagine that we're reflecting here over this horizontal x-axis. So for instance, this point here, -3, 2, that +2 value for y would flip over and become a -2 value for y. Or over here, this -2 for y would flip over the x-axis and become a +2 for y. So we're just multiplying all of the y components by -1. So to accomplish both of these, we need -x and -y. So this here sort of describes our transformation in the same way that this expression over here on the right-hand side of this equation expressed the transformation. So now we just want to put this into a transformation matrix, and we do that by figuring out how this transformation affects our standard basis vectors for R2, I, and j. So we want to know what this transformation does to the vector 1, 0, the vector I. Well, if we plug 1, 0 into this -x, -y, we're going to end up with -1 and then still 0, -0, but that's the same as 0, so it's just -1, 0. And then what does this transformation do to j, the vector 0, 1? Well, the result there is just going to be -0 or 0, and then -1, so -1. So we put these together with I first, -1, 0, and then j for the second column, 0, -1. And this is our transformation matrix. Now we can use this, multiply it by any of our vertex vectors, and get the transformation of each of those. So let's say we multiply this by first the vector 4, 1. When we do, we'll get, as a result, -4 plus 0, that's just a -4, and then 0 and a -1 is a -1. When we multiply that transformation matrix by 0, 4, we'll get 0 and 0, it's going to be 0, and then 0 and a -4 is a -4. When we multiply that matrix by -3, 2, we'll get a +3 and a 0, so that's a +3. And then a 0 and a -2 is a -2. And then when we multiply it by our last position vector, 1, -2, we'll get a result of -1 and 0 is a -1, and 0 and a +2 is a +2. So now we can think about this as our 4 position vectors here for our new quadrilateral, our transformed quadrilateral. And so if we sketch those, we'll start at -4, -1. That's that point right there. Then we have 0, -4. That's this point right here. Then we have 3, -2. So 1, 2, 3, and a -2. And then -1 and 2. So that would be -1 and 2 here. And then we can close that. And we'll get the transformation of the original figure. And we can see, in fact, the reflection over the x-axis and over the y-axis. Because if we start with this point, 4, 1, if we reflect it over y, we would get -4, 1. And then when we reflect it over x, we get -4, -1. And that gets us to this point here. When we reflect this point, 0, 4, across x and y, we get this point right here, 0, -4. When we reflect this point here, -3, 2, we get this point here, +3, -2. And when we reflect this point, which is 1, -2, we get a -1, +2. And that's where each of these points ends up after the linear transformation that we were able to express as these matrix vector products.